Okay. Okay. Hello, everyone. Assalamu alaikum. Good afternoon and good morning in Canada. Welcome to the CAM seminar series. I'm glad to be the first of this year. I guess this is the first one, the very first one. It's January 9th. This is Muhammad Hassan from Center for Advanced Materials. We are glad to have Dr. Ayman Al-Haj from University of Waterloo with us joining us today. We're supposed to have Dr. Rifat Ghunaim from National Research Council in Canada, but he could not make it. And we will present some of the data, the results that we have together as an MBRB project and also IRCC project between Qatar University, University of Waterloo, Texas A&M at Qatar. We have also Dr. Ahmed Abdullah and Dr. Lina Suleti, of course, from the CAS, and Dr. Ahmed Masoud from the Chemical Engineering Department. So this project is on development and evaluation of nano-based silicon rubber composites for high voltage insulations in Qatar environment. So it has a multi-component. It's a multi-component project that include mainly electrical engineering aspect, and it addresses one of the major issues, like an issue of major concern for Kahrama, for example, and the insulation industry in Qatar. And also it has a material science aspect, and also it has a chemistry aspect as well. Also, we are glad to have a very good support from Kahrama. We thank them for this. And of course, we thank QNRF for and Qatar University for the funding of the two projects, as well as CSL siloxane or silicones in Canada, which is manufacturer of these similar kinds of coatings that is used for high voltage applications as insulations for high voltage applications. We're also glad to have Dr. Rifat Ghunaim from National Research Council of Canada as part of this project as well too. So it includes the three main aspects: chemistry, material science, and electrical engineering. So just like an overview of our project has mainly two big components. One of the components is to form a new type of coating that will survive under the harsh conditions of Qatar, and it will act as insulators for the high voltage applications. And it's based on polydimethylsiloxane or silicon rubber, or what we call like RTV, room temperature vulcanized silicon rubbers, and mainly polydimethylsiloxane that is filled with either acting by itself or and mostly it will be filled with some kind of filler, either in the nano filler or a micro filler. And we mainly produce the fillers. You see, like this is like a typical sample that we make in labs at Qatar University and also at Texas A&M with Dr. Ahmed Abdullah's group. We spray coat the coatings, whether that coating has a filler or not. We spray coat it on a ceramic. This is a ceramic, typical tiles that is accepted by the community, the electrical engineering community. And we coat our coating on this kind of tile, and we make like these three holes in order to later on test the performance of the coating using what's called IBT test. We will talk about these kind of testings, electrical engineering testings, in details, and Dr. Ayman will introduce and like explain to us this kind of electrical engineering testing, because they are a bit hard for us to understand. We are trying to catch up with them, but very interesting and very meaningful in terms of material science. And we hope that you all can learn a bit together with us, whether you know these kind of testings or not. We also typically also measure the morphology, the thermal stability. Very important aspect is the surface hydrophobicity of the coatings that we develop, and also the mechanical strength of those coatings, and link all these parameters together to obtain like a high performance coating that is developed by us, and hopefully we can apply it in the industry later on here in Qatar. Another important aspect I mentioned at the beginning, there is two major aspects, which is developing of our own coating to compete against the industrial one, of course. And the other important aspect is to evaluate the industrial ones that is currently used by Karama. And those are pictures, actual pictures of insulators that are that were provided kindly, very kind, and we really appreciate the help from Karama and their support in this project with all the technical aspects and providing this kind of insulators. Those are actual insulators that have been there in the field for certain amounts of time. And you see, like we scratch them and we try to analyze what happened exactly to the commercial coating and to understand how the environment in Qatar affect these kinds of coatings. Mainly, we look at the SCM and EDAX to track the roughness, physical damage, and also the concentration of different elements like the silicon, oxygen, carbon, and aluminum with time under weathering conditions. Also, the thermal stability after the exposure to the Qatari environments. FTIR to see if any chemical degradation happened to these kind of coatings. Also, the aging, we after this, we quantify the aging degree and what we call like health index, the coating health index. This is to help the companies like Karama to measure how many times they need to recoat these insulators in order for them to continue like doing the function that they are for. Also, we are trying to understand what are the main parameters that is mainly responsible for the degradation. At the end, this is a silicon rubber or polydimethylsiloxane that will degrade under the harsh conditions. Under combination of the harsh condition and also the electrical discharge, the surface discharge, or what is called in the electrical engineering the leakage current. There will be some kind of flash or flashing that happens with time, and Dr. Ayman will speak about this in details. So we are trying to understand the combination, the effective combination of those kind of flashing with things like rain, temperature, and UV and pollution and so on and so forth. For example, the CO2 that is present in some places in Qatar, or maybe some salt in the fog, or maybe some sulfur dioxide. These kind of things. We are trying to understand all of these parameters and analyze the material in terms of material science, in terms of chemistry, and in terms of the aspects of the insulation aspects, the electrical engineering, just to understand exactly what happened to those coatings under exposure to these kind of environments. So I will give the floor now to Dr. Ayman to tour us through the electrical engineering part, which we are all like trying to understand in a good way, inshallah. Dr. Ayman, please.
Thank you, Dr. Muhammad. Assalamu alaikum, everyone, and good afternoon. It is my really pleasure to be there with you. And Alhamdulillah, this is my third NPRB project with Qatar. So it's since more than 10 years now, I'm working with the Qatar University in different aspects. Okay, so we'll start with a certain of background so that we are all of us are in the same ground so that we understand why you are doing this project, what is the importance of this coating. To start with, we're starting with the electricity. When we produce electricity, we produce it at a very, very high voltage so that we can reduce the current in the lines and hence reduce the losses. Most of the power that we produce and we transmit, we use what we call overhead lines, like the ones that here shown in the picture. And these overhead lines, you can see here the conductors that carry the power, and the tower for the support. And between the tower and the conductors, we have the insulators. So these insulators' main objective is basically to mechanically hold the line. That is the main objective. But to do that also, they have to electrically insulate the high voltage from the ground. if they cannot do this job, then there will be a flashover or an arc from the high voltage to the grounded tower. Now, these insulators, they have to do this job under severe environmental conditions, like the ones that we have in Qatar. It's under humidity, under UV, under sun, heat. So there are many factors that influence their performance. Next, please. The old technology that has been used as an outdoor insulating material was ceramic, either porcelain or glass insulators. And now we have more than 100 years of experience of those insulators. They are very stable material. So when the arcing I just told you about, if an arc happened on the surface of the material still has its own integrity and can withstand the heat dissipation coming from this arc. However, there are two main disadvantages of this material. The first one is the heavy weight. As I have shown in the previous slide, that those insulators, they has to be hauled by the tower, so they have a mechanical burden in the tower, so the tower has to be strong enough. And now as we increase the voltage, the length of these insulators increases more and more. It means that more and more mechanical burden. So since the 70s, when people start to increase the voltage for transmission up to 1 million volt, they start to think about a different technology with a much lighter weight that can hold the conductor, but at the same time doesn't have this mechanical stress on the tower. The second problem, which is more severe, is the contamination performance. These materials, because of their high surface energy, they are hydrophilic in nature. So what does mean that? It means that they are easily wetted. Whenever there is a wetting, like for example, in the early morning here, for example, in Doha, we have a humid environment. So you will have dew condensed on the surface. Now, these insulators are subjected to the environment, so there will be a lot of pollutant on the surface. Now, humidity, pollutant, and if your insulator near the sea, or the coast, then those pollutants, they will have sort of salt in them, like in ACL. So this NaCl start to dissolve because of the water. So now you have a perfect environment to start conduction between the high voltage and the ground, which will lead to the flashover. Next, please. When we say what is a flashover, this is two demonstration, as I mentioned. Now, when the surface becomes wet, wet with a pollutant that has certain electrolytes, then you'll start to have an arc like this, or like this one. And this arc will lead to disturbance with the power system. This is considered as a flashover or a failure in the system. Now, the power system is protected. There is a protection system that will when these things happen, they will disconnect the line, but to prevent fires. However, when you disconnect the line, this is an interruption to the power system. We lose power. This is one of the major reasons why we might lose power in overhead lines. 60 to 70% of the failures of the overhead lines is because of these insulators flashover. Now the question is how we can control this. We don't want to have this current developed in the surface, so how we can solve this issue. Next, please. So there are the first one of the major solution is to use non-ceramic insulators, and we'll talk about that. What is the pros and cons of that? And as I mentioned, the major incentive for using a different technology was the very heavy weight of the existing technology. So people start thinking in that direction, and then they came up with the hydrophobic material, and we'll talk about that. The second thing is with the existing solution that we have, which is the ceramic insulators, and I said we have very long history of use. What are the solutions that we can deal with it? There are a couple of solutions like washing, application of grease, and the RTV coating. So we'll go through each of those solutions and try to explore together what are the pros and cons of each of those solutions. Next, please. So let's start with the non-ceramic insulators. Non-ceramic insulators are, they have completely the opposite uh, properties of the ceramic insulators. The first obvious property is the lightweight. For example, in 400 kV insulators, we can reduce the weight by 90%. So you can see how much mechanical burden we can save. So this is a big advantage. Second advantage of these insulators are vandalism resistance. What do we mean by that? Ceramic insulators or glass insulators, they are brittle. So for example, if you take them to the site and if they fall on the ground, they will damage. But those insulators are basically made of what? Made of, internally, there is a fiberglass core, and on the surface they are encapsulated with the silicone rubber material, as you can see it in these two examples. So if they fall in the ground, the rubber before that, okay, the rubber will take the mechanical shock, so they will not be damaged. Now, more important than these two properties is the hydrophobic behavior. So if you see here, because of the low surface energy of these insulators, and if these insulators are wet, you can see here that the water droplets, they are not connected together and they are very, very discrete. This behavior will prevent the development of the leakage current. However, there is no perfect material, as we know in engineering. So first disadvantage is aging. Their long-term behavior under severe contamination conditions still known in some countries and not known in some other countries. Now, in the Gulf region, we start to adapt this technology in the, for example, in Saudi Arabia, they start to use in the last few years, maybe 10 years now, they have history, and they have some problems. I will talk about it in the coming slide. Next, please. This is an example of one of the Gulf countries. They are using polymer insulators. And unfortunately, this is a case of severe aging that happened to the watershed material of the silicone rubber. And once these materials start to age, they start to erode, then the fiberglass core will be start exposed to the environmental conditions. The fiberglass core is not well protected against environmental conditions, so there will be some damage them, and until the fiberglass, something happened, we call it brittle fracture. They will fracture, and the whole line 400 kV will fall in the ground. And this is extremely bad, as you can imagine. 400 kilovolt lines fall in the on the ground, and for in this specific overhead lines, 3 to 4 incidents I am aware of that happens with a similar thing, that a 400 kV line fall in the ground. So yes, non-ceramic insulators can be very good solution, but in countries that the weather condition not that severe like our countries. Next, please. So let's go back to the ceramic insulators. How to deal with them? The first solution to this problem was washing. Okay, and all the countries in the Gulf 30, 40 years, they were using ceramic insulators. Okay, so how to deal with this pollution that start to accumulate on the surface? You have to wash it. Okay, after you wash it, there is no pollutant, everything is good. What is the problem of this? The first of all, imagine washing those thousands and hundreds of kilometers in the desert. How much the cost involved in that? This is number one. Number two, the safety. You are washing insulators, it is deionized water, but this is one of the most dangerous jobs you can have. Number three is that we don't know actually technically how often we have to do that. Sometimes we do it too often, which is very costly, and if we don't, we have a flashover incident. So this solution, yes, effective somehow, but it is very costly and it's not an optimized solution. Next, please. Then people came up with another solution, is to use sort of a grease to cover the ceramic insulators. and they use some materials. The last one they use is the silicone grease. Now, the silicone grease will encapsulate the pollutant, will prevent the flashover, which is a perfect thing. However, people start to realize that you need to replace the material after 1 or 2 years. And imagine removing those grease materials from the insulators, and we have millions of those insulators. So how tedious is the job? So that's on the short term is a good solution, but for the long term is not a good solution. Next, please. Now, then came up the solution of the RTV coating. The RTV coating basically is a room temperature vulcanized coating made from silicone rubber, the same material we used for the non-ceramic insulators we start with. So you come up and you spray the insulators, and you will have the advantages of the surface with the low surface energy or the hydrophobic surface. And in many countries, it has been reported that 7 to 10 years is the age, which is something very good. The good news here is that for 7 to 10 years, you don't need to wash the insulators. It is maintenance free. So all these costs that in some places, I know, for example, in Saudi Arabia, in some places you have to wash the insulators every 6 weeks. So imagine the cost involved now with just going and coating these insulators. Then that this is a big advantage. Next, please. Now let's come to Qatar. How Qatar Kahrama use this technology. They use it in a bit a different way. They don't go to the site and spray the insulators, but they use what we call a pre-coated insulators, as you can see here. So basically, they use glass insulators, the one that Dr. Muhammad showed at the beginning, and then these insulators are pre-coated and then used in the field. So there is no coating in the field, because coating in the field, it's very hard to control. So this is the technology used now. Now, what is an RTV coating? It's basically, it is a polymer material, polydimethylsiloxane base. There is a cross linker, there is a colorant, there is fillers. We use filler here to enforce certain mechanical and electrical properties. We use fumed silica for mechanical integrity. We use aluminum trihydrate, ATH, for better thermal properties for the material. We use adhesive promoters so that we have a very good adhesion between the coating and the surface of the glass or the ceramic insulators. So this is a sort of introduction about why we reach to this RTV coating business. Next, please. Now, I will talk on behalf of my colleague at the NRC. He prepared some slides about the effect of the fillers on the insulator. So as I said here, ATH is the main filler used by industry, and they use it by 60% by weight. And this ATH material has a big advantage in two different aspects. First, once you start to have an arc, when the material age with time, they lose gradually their hydrophobicity, and then there will be some arcing on the surface. Now, once you start to have some arcing, the ATH will release what we call the water of hydration, because ATH is alumina and water particles. So once they start to release the water, it quench these arcing. So they have this mechanism that can help to remove or to reduce the effect of the arcing. Second, they improve the thermal properties of the arcing. Next, please. Now, here it is sort of a demonstration showing the lifetime of these silicone rubber insulators. As I said, they age with time, and when they start, for example, you have those insulators in the country like Qatar. We have a very high ultraviolet. The UV radiation age those coatings, and then gradually they will start to lose their hydrophobicity. Then they start easily weighted. Then you have the leakage current. Now, once you start to have a leakage current on the surface, certain parts will have higher current density than others, so you will start to have dry bands. Now, these dry bands, they will have very high electrical stress on them, will lead to what we call dry band arcing on the surface, and this dry band arcing will lead to the erosion of the material. Next, please. Now, how to test this material during the development stage? Since the 60s or even before that, people came up with this test called the inclined plane test. So this inclined plane test is to use it to test both RTV coating and to use also HTV, high temperature vulcanize, the material used for the full insulators. So this testing is as per IEC 587 and ASTM D2303. In North America, we use more the ASTM standard. In Europe, in the Middle East, we use more the IEC standard. So basically, what is this test? You have the samples. These white material are the samples, and here this is the samples of the silicone rubber. We have it at 45 degrees. Then we use peristaltic pumps to gradually pollute the surface or wet the surface with a conductive material. So we will have these peristaltic pumps, and you can see it from the top of the samples, and these are some papers. They will be wetted so that you will have a smooth flow of the water. You will not have a pulsating flow of the water. And then you will have here coming, this will be a high voltage, this will be a ground end. So now you have a high voltage, you have a ground, you have an electrolyte, then you will start to have arcing. And we do the test with certain protocol. And if the material, and we'll talk about the criteria of the fail and pass in the coming slides. But now we keep this for around 6 hours, and then we test that, we check if the material is good or not. And there is a standard test at 4.5 kV, and we keep the testing running for 6 hours. Next, please. Now, these are two samples. This one, the passed one, and this is to the right is the failed one. Now you can see here some traces of tracking and erosion. Now, what is the criteria for the pass and fail? If the length of this arcing from the ground end, which is this side to the top, is more than 2.5 centimeters, we consider this material is failed. Or if there is a puncture in the material, sometimes we don't have this long erosion, but we have a concentrated arcing that will lead to puncture of the material. So this material will be failed. But if none of the above happened, then we consider the material as passed and consider that the material can be adapted by the industry. This is the main test. We call it the material test that can be used to screen the different designs of the materials. Next, please. Here is some research happened at the NRC. Now there is an interest to use high voltage DC as well, and high voltage DC has certain advantages. Uh, of course, the main theme of the transmission is an AC system, alternating current system. In Qatar, all the system is AC, but in certain places where you need to transmit the power for a very long distance, then you need to use DC, direct current, meaning that it has only one polarity. Another advantage of the DC, when you want to connect countries with different frequency. For example, there is a link between the Gulf countries. Saudi Arabia has a 60 hertz. The rest of the Gulf countries has 50 hertz. How to connect two network that has different frequencies? We have a DC link between them. So from Saudi Arabia, 60 hertz, we convert it to DC. Coming, for example, to Qatar or to any other Gulf countries, we convert it back to the 50 hertz. So this DC link is needed when you have different frequencies between the countries. And this makes some more challenges on the design of the material. So these are some research were done at the NRC trying to test different fillers under AC, under DC as well. And you can see here the erosion under DC is more severe. Why? Because In DC, we have only single polarity. The DC by itself will even attract more of the pollutant. So the design of the material has to be looking differently when we design for DC. We were working with some colleagues all over the globe. We developed a standard for how to apply the inclined plane test using DC, and the standard has just been released. This is something Dr. Muhammad will come to back to it later on, and this is something very, very important, that once you start to have arcing on the surface, then there are two phenomena will take place: tracking and erosion. Tracking, when you have a carbonized path on the surface, which will even enhance more the development of the leakage current. Why? Because carbon is a conductive material. So this is extremely bad. And one of the reasons using silicone rubber as non-carbon based polymer is to avoid this carbonized or this tracking. However, because of certain mechanism, maybe Dr. Muhammad will talk about it, tracking still can happen, but erosion is the main thing that happens in silicone rubber. The material just erode from the surface without the tracking, and the mainly we were testing the tracking, sorry, the erosion ability of silicone rubber. Next, please. Now, here it is. What are the challenges when we design the material? As I mentioned, okay, we need to develop the material, subject it to dry band arcing, and then analyze the material, what is happening on the surface. Now, this is, we call it the erosion resistance, but the erosion resistance is just one aspect of the material. There are some other aspects. We talked about a very important aspect of the silicone rubber. It is hydrophobic in nature. However, with time, they lose this hydrophobicity. However, silicone rubber have this ability to regain the hydrophobicity. How? They have what we call the low molecular weight that can diffuse to the surface of the material and regain again the hydrophobicity. Now, how long we can have this reservoir supplying this material? Some researcher decided or mentioned that the end of life of the coating, when we don't have this supply of this material, how the material design can impact this hydrophobicity recovery. These are very important aspects and need to be taken care of when you design these materials. Next, please. Now, this is another illustration to show this whole idea of how the environment, how the surface, how the pollutant, all of them, they can be having synergistic effect to damage the surface of the material. So here we have the silicone rubber material, and we mentioned that when you have dry bands, then you'll start have to have a dry band arcing. So you have an arcing in the presence of oxygen on the surface of the material. We have a plasma, because the arcing here will be have a very high temperature, can reach hundreds of degrees centigrade. So this will cause some erosion, some char on the surface of the material. The main challenge is now how to develop a material that will resist the erosion, resist the damage of the surface under this huge or under this very high stresses. Next, please. I think this is my final slide. So this is what we have. This is like a sort of like a flow diagram, what is happening on the surface of the material. So we have the silicone rubber material. Okay, now you will have the DBA, the dry band arcing will start to take place. You will have a pyrolysis effect on the surface of the material. You will have combustion because you have this dry band arcing under air. Now this will come back, and this cycle will stay going on until the material is completely failed on the surface. Our objective is try to develop a material that can withstand this cycle as for the prescribed time, which is 7 to 10 years. I want to make one last comment here, and something very important. is that in our countries, the environmental conditions are totally different than, for example, in North America. Now the temperature here today is around minus 15 degrees centigrade. So this is another challenge that we have here in the environmental conditions. But in our country, we have humid, we have high temperature, high UV. So this is another different aspect. So as researcher, it's not just good enough for us to just adapt a technology from the West, but we need to take it to our environmental conditions, maybe came up with our own formulas that is more suitable for our environmental conditions. And this is what we are hoping to achieve with Dr. Muhammad and the team in Qatar. I think that's my time. Thank you very much for your listening.
Thank you, Dr. Ayman. This is very great explanation and educational section of the workshop or the seminar, actually, because maybe I don't know how many electrical engineers are attending, but at least my knowledge that the majority are material scientists and chemists. So thank you so much. Just to continue our presentation and our seminar today, we preferred actually to have this kind of interactive and like multi-person setup, just to present to you the comprehensive, like the whole picture actually, from different perspectives. One, as we mentioned, there was initially like mainly two big aspects: is to develop our own coating that fits and works better for Qatar environment, and the other aspect is to say what's happening to the existing coatings that has been installed by Karama for a long time. One of the things that one of the biggest questions actually, that typically the commercial coatings, they typically use like a certain material, certain type type of PDMS, polydimethyl siloxane. In terms of material science, as a material scientist, like a polydimethyl siloxane material has many different molecular weights. So we thought, in discussion with Dr. Ayman and Dr. Rifat and Dr. Ahmed Masoud, our colleagues from electrical engineers, we told them, okay, but there is so many different types of molecular weights. So which one would be best? So this was one of the biggest questions, and we thought like we are trying to answer through this study is which molecular weight would fit better for the ultimate application actually. Why did the commercial vendors choose certain molecular weight? This is a big question. Of course, I asked Dr. Ayman and Dr. Rifat that question, and it seems that it's not actually known by the electrical engineering community. The vendors, they don't tell the exact molecular weight, right, Dr. Ayman? Or yes,
Definitely. This is considered as one of the secrets, the industrial secret on the formula.
okay.
But this not are revealed. Yes, you're right.
Yeah. So this is like why did it choose this or that? We don't know exactly. Or one of the things, as Dr. Ayman mentioned, so we thought to do like a very molecular, very basic study on like just different molecular weights. What is the effect of different molecular weights? And of course, those are all what I will present right now is all unfilled. It's a data for unfilled. The material does not have any filler. And later on, we'll continue the same study with different fillers. Also, another important aspect of this project, as I mentioned in the very first slide, few slides, those pictures from Karama insulators. Unfortunately, we still working with our colleagues in Karama, and we appreciate their support, as I mentioned. We cannot just disclose any data. We have plenty of data on this too, but we cannot just disclose it to you at this point. We're still working with them on this part. There is another important part that is mainly done at Texas A&M with Dr. Ahmed Abdullah's group, like trying different fillers and different fillers functionalization. And I will talk about parts of this. Dr. Ahmed is with us today as well too. If you have any question at the end, he will be able to answer them as well too. We designed like a system with four different molecular weights, and very much those are the ones that is very much available in a commercial scale from GLAST, the American company, with variable. We meant to vary the molecular weight as you have seen, like as you can see. 9,000, 17,000, 28, and 45,000. And we made the spraying on the ceramic tiles. And this is how the chemical reaction, of course, if you are a chemist, you see like we use polydimethylsiloxane. The molecular weight would be like different molecular weights would have different number of ends, number of monomer units. The N will be different from one to another, and so on. It's mainly it has a divinyl, and the crosslinker, which is this one, it has SiH group, and the SiH group would need a catalyst. But we use a platinum catalyst. The platinum create radicals, and the radicals attack there at the double bond, and then the SiH group will add in an addition reaction to these groups, and it forms the cross-linked structure. This is basically what's happening in this reaction. This reaction would take about from half an hour to like 2 hours at most, I guess, to fully form the coating, and the coating will be dry by that time. Of course, this mixture to facilitate as I mentioned, we coat it, we just spray coat it. To facilitate the spray coating, we typically use a solvent, and this is exactly what the industry does too. They typically use a solvent, and later on we'll add also like adhesion promoter and the other components that the industry uses. But for this very basic study, we thought like just add the main components without any other things to just to simplify the the understanding of what's happening. Uh, so yeah, it is done through spraying, and we use the ceramic tiles, which is typically accepted. And for those coatings, we started to look at the material science part, the material characterization part. This is typical TGA. TGA is very important in this kind of application because the thermal stability is very important. When arcing happens, electrical arc, when it happens, it mainly creates heat, and this heat, the dissipation of heat, is very important. So the thermal conductivity is very, very important, or the thermal stability of the material. The first thing that, as you can see, there is a big difference between, for example, the very high molecular weight, which is the black curve. It has a 2 degradation step, as you can see. And the pink color one, which is the lowest molecular weight, it almost has a 1 degradation step. And this is very, very important in terms of understanding the mechanism of degradation of these kind of coatings when you apply the IBT test. So through the discussion with Dr. Ayman, Dr. Rifat, and the rest of the colleagues, we thought, okay, there is two things that is going on there in terms of mechanism. There is a depolymerization degradation that happens through a depolymerization step or the radical cross-linking step. So the low molecular weight, it seems that it has a more tendency, the high molecular weight, sorry, it has a more tendency to do two different steps through what is called the radical based cross-linking. In terms of the radical based cross-linking, what's happening is you like form like a cross-links. After you degrade, the heat will form additional cross-links, and eventually it will form a silicon carbide or a silicon oxycarbide layer. And we actually confirmed this with the TGA FTIR. In the next slide, you'll see it. While the depolymerization one will turn to have more carbon, and this is what happens in the lower molecular weight one, the pink one. This is why the residue for the high molecular weight one is more than the residue for the low molecular weight one, because of this silicon oxycarbide. It's a thermally it acts as a shield to prevent further degradation into the material. Yeah, and we confirmed this through, you see, like we analyze the TGA, the effluent, evolved gas analysis, the gases that form due to the degradation in situ. We have here in CAM, we have the TGA that is attached to the FTIR, and we analyze at different temperatures what happens. And we, with the intensity of these different peaks, we decided that for the low molecular weight ones, we have a more of silicon oxycarbide or silicon carbide. This is based on intensity. It doesn't clearly show in this one, but if you compare the intensities, you will be able to get this point. And actually, this is for one sample only. Sorry, it's not like comparing the different samples. Just to show you like what we do exactly. So you take like a sample of the evolved gas and you do a FTIR at different temperatures. The machine does this actually for you. And we have this capability here in CAM. In terms of the IBT test, you see like the low molecular, this is the high molecular weight and this is the low molecular weight. They are not compared at the same time, but the high molecular weight seems that it has tendency to track, as you can see in this. But in the case of the low molecular weight, it has more tendency to erode. And there is like a very clear, behavior or very clear trend of difference between the high molecular weight ones and the low molecular weight ones, and it is linked to the depolymerization versus cross-linking tendency, as I mentioned earlier with the TGA. So we think like in case of the high molecular weight, chains are longer and are more restricted. And this is why they tend to form like a radical-based cross-linking is preferred in this case. This is just to understand the mechanism. But the low molecular weight, the chains are more restricted because the chain there is more cross-links. There is additional cross-links in the low molecular weight one. The cross-link density is higher in case of the low molecular weight network. Low molecular, and as you know, like for this kind of system, BDMS is cross-linked from the end. So the entire chain is the molecular weight between cross-links, or the chain is entirely cross-linked because it is hogged from the both ends. It's not hogged across the chain, like in case of butadiene rubber, for example. In case of butadiene rubber, the cross-linking happens across the chain. But in this case, it's end linking. We call it end linking, or it's not really cross-linking. It's end linking. You link the chains from the end. So the entire chain, length will make a difference between the high molecular weight and low molecular weight. In this case, we have 45. The chain is 45 gram per mole between the two cross-linking points. But in this case, in the lower molecular weight, we have about 10,000 or 9,000 gram per mole between the cross-linking ends. But in the same time, the degree of cross-linking is much higher in case of the molecular weight, which restrict the motions. So the chain motion is more restricted, sorry, in case of the long chain, not in the short chain ones. This is just to show you like what happened exactly with time, because we do the test, we apply the 4.5 kilovolt, and we see like how much the sample will handle until like it make a big failure like this in this case. So up to what limit the sample can handle, and this shows you like very much the trend of all. There is a variation of the IBT behavior versus the molecular weight effect. So the molecular weight definitely is worth of the study, and we have to consider it. We have to take this into place. Of course, we tracked, just to give you an idea, this is the contact angle. The highest molecular weight has the highest contact angle as expected. So this is all known. But also there is a difference in the contact angle that might also eventually affect the IBT and the surface stability or the erosion stability with time. The mechanical, just to understand also if the mechanical has any role, there is difference as expected in the mechanical strength of these different coatings. Now for the silica filled ones, we choose one of the molecular weights and we vary the filler. We used different strategies and different filler contents and so on. So first we used the fumed silica that we got from one of the companies here in Qatar actually, and it is very much like a waste. and we use it in this application on a hope to we just hope that to reduce the cost of the overall coating using this kind of waste silica. And also we use boron nitride, hexagonal boron nitride also as well. We also did like two different kinds of treatment, like a physical treatment, like ball milling and exfoliation without adding any chemicals. For the ball milling for the silica itself, on like an attempt or to reduce the particle size of the silica and try to reach the low molecular weight, I mean the nano range, hopefully. Also the exfoliation also to affect the particle, the HPN is more like sheets. So we are trying to exfoliate these sheets using the silication and isopropanol. And another effort is going on to also to functionalize the silica itself. Typical loadings we use from 20 to 60, and this is an actual sample with the filler and the PDMS. So the physical treatment, as I mentioned, is a ball milling to reduce the particle size and to get a better dispersion of the filler within the PDMS matrix. And the exfoliation will do the same thing too, just trying to understand if the exfoliation will have an effect in this kind of application. And this is the chemical treatment using triaminopropyl trioxysilane to enhance the thermal stability, better dispersion, and also this is very much compatible. Based on the literature, it's highly compatible with BDMS. Many people are using it already. Another treatment is to increase the hydrophobicity of the silica itself before you put it into the matrix with using like a bare fluoro chain. And so you hook this side to the silica as a nanoparticle, and this chain will be dangling. And this is in an effort to increase hydrophobicity and hopefully to the better stability. Also, another strategy is to functionalize the silica itself with oligomers, low molecular weight oligomers. Through like, the silica has plenty of OH groups. So we are trying to like hook like a BDMS chain from one side to this silica. So in that case, you get much better dispersion in the silica within the BDMS matrix. So I'll present some of this also for the sake of time because we almost 1 hour now. So this is like quickly some of the samples, like SEM analysis of the surface and the fracture, freeze fracture surface, the cross section surface. In this case, just to show you how the silica looks like inside this kind of matrix. This is a TGA, also like very much. This is a very typical curve for the commercial ones as well too. The remaining weight percent is very much similar to what we typically get from the commercial. If you run any commercial coating, you get very much the same curve. This is the hydrophobicity before any aging or before any testing, very much within the range that is the expected hydrophobic range. And this is the IBT test. For those samples, we're still working on them, of course, but we did some screening. And this is a screening test, basically. It's not the samples that I presented before for the different molecular weight were like fixed, 4.5K fixed until the failure happens. In this case, we do increment like 0.5 kilovolt every 30 minutes. And this is to evaluate what happened to the voltage, or we were trying to understand at which voltage exactly the tracking start to happen. So this is a control BDMS, and see like it can handle up to 4 point, it can reach this 4.K voltage, but this is just like an increment test. It's a screening test. This is not the typical one that is supposed to happen according to the standards that Dr. Ayman mentioned about before. Actually, this is HPN ones. Very much also they are okay up to certain kilovolt. Another sample of HPN. I'm just going through them and I will show you the comparison how the filler can affect the results right now. For example, this is a fumed silica up to like start to have something around 3.5 kilovolt. This is ball milled fumed silica, and this is a comparison that I want to reach actually. So the at 4.k just as a comparison around 4.k kilovolt, you see like there is a difference actually in the difference the HPN or the fumed silica and the ball milled fumed silica is very much like acting much better than the fumed silica itself. I'll show you the results. Why is that? This is the case right now. And in this case, actually, also it is much better than the HPN at this point. This is like just to show you like after the cleaning, because sometimes you get some char, but that char is mostly because of the conductive electrolyte. We add, Dr. Ayman mentioned, we add some kind of conductive, the triton conductive electrolyte to make the surface conductive. And sometimes what is burning actually is this conductive electrolyte. It's not the coating itself. This is why we clean it and to make sure that this is not the case. That what is burning is actually the coating, not the conductive electrolyte. Then we talk like we analyze the hydrophobicity, what happened to the surface hydrophobicity at 3 different spots: the side of the erosion, and in an area where no erosion, which is very much should be similar to the contact angle before the erosion, and also at the top of the erosion point. So like in the areas where no erosion, you see like here, very much the contact angles stay the same, very much for all the samples. No change happens actually in those areas. But if you, the biggest change happens in the area where the erosion happens. You see like in these kind of spots. So the biggest difference, and this is why I mentioned earlier that the ball milled fumed silica is acting much better because it's still maintaining its hydrophobicity after the erosion. You see, like the fumed silica without milling, somehow it dropped a lot actually after exposure to 4.5 kilovolt. And same thing for this sample. We need to see what's happening on this. We need to repeat these two because these are supposed to be the same sample actually. But just if you just ignore what's happening here, like for the BDMS, it's the same thing too. It does not maintain its hydrophobicity after erosion. Like, and this is the test was done like maybe it's not more than it's not more than 4 hours until you reach that 4.5 kilovolt. But it lost its erosion comparing to something like fumed silica, for example. And this is a very important point to take into consideration. At the side of the erosion, also very much nothing really happens, nothing much, but and it's because it does not get exposed to the electrical charge as much. Just to make the long story short and not to take too much of your time because we are running out of time already. So we have plenty of data to present, and like anybody is welcome to discuss any kind of the results that the other results. We looked at different systems and throughout this study, and we analyzed so many samples. But for the sake of time, we just meant to present these two examples for you and to introduce you to the IBT test, the electrical engineering part. We are glad to have with us many undergrads from CAS, from the chemistry department, and we are really happy to have them with us. They have been working very hard and they absorbed many of these tests and they understood many of the aspects of this project. And just as a conclusion and summary and the future plans for us. So we have been testing actually many things for the erosion and tracking of the coating. Also, We considered many parameters, and we tried to answer one of the most important questions, which is not answered yet, especially in the electrical engineering community, which like the effective molecular weight of the matrix itself. Not many studies are there for in the literature for just like looking at the matrix itself. The matrix itself also is a very important aspect. Also, the catalyst loading is a very important thing that we looked at. Filler and physical and chemical treatments of different fillers, and we are also working hard to reduce the cost of the coating through different fillers that is out there as a waste. We have other types of fillers that is out there as a waste, and we tested them as well. Also in the contact angle measurement is very important for us, as well as the IBT test and the thermal degradation, because it's very important for the coating to maintain its hydrophobicity, as Dr. Ayman mentioned, for the diffusion of the polydimethyl siloxane to the surface. And this is also should be affected by the molecular weight between crosslinks. The different molecular weights will have a diffusion capability, different diffusion capability. I mean, it will that diffusion will be affected by the molecular weight. One of the important tests that is still in progress, and we'll send those samples to Dr. Ayman because he has this test, is a salt fog test. So the salt fog is a combination of multiple things. In this case, is erosion and tracking. You have seen the voltage and possibly the humidity and temperature, but also Dr. Ayman can expose it to UV and salt fog for 100 hours test. This is a typical test, and this will combine so many things. And he has a setup there in Waterloo. Uh, Also, the corrosion resistant, the corona resistance test is another aspect too. This is something that we could do. So this is like, honestly, I don't understand this in a quiet bit, but this my understanding. It's like 10 to 12 kilovolt applied for like about 2 hours, 12 hours, sorry. And in the presence of, it's not a corona in the sense of Dr. Anton. I know he has a machine to produce the corona, but I don't know if that machine can reach 10 to 12 kilovolt. Maybe Dr. Ayman can comment on this at the end. So this is another test in progress too. So just to get a complete understanding and a complete evaluation for the coating from different perspectives. And once we complete these different tests, we'll be able to see like, okay, this coating can proceed to the next step for the like the commercialization step and so on, so forth. So with this, I would like to thank like people who does the work. Actually, we're just sitting in our offices, as you know, as everybody does, and most of the work is done by our graduate students and RAs and so Fadi, Bilal, many thanks for both of them. They did a great job in the molecular weight stuff. Medhat and Shabari at Texas A&M, Qatar. They did a great job on the silica field and different the HPN field ones. Basharat and Khadija from Dr. Ayman's group as well. We thank them they did quite a bit too, but for the sake of time, we could not like comprehend everything in one single presentation. Also, the undergrad, Ahmed, Nagla, Fawziya, Safa, and Sarah, we appreciate their participation. We thank Karama specifically for providing samples, providing technical ideas and technical support to us on the behavior of the commercial ones, and also the CSL Canada Silicones, which a company that sells the commercial coatings to the Gulf region in general. And we have agreement with them to hopefully, if something works, possibly we can commercialize it somehow through them, hopefully, inshallah. Yani. Most importantly is to thank QNRF for the very generous funding and Qatar University for the IRCC funding as well too. Dr. Ayman, if you want to say something, and Dr. Ahmed Abdullah, you are with us today too. If you can hear me, if you want to say something, please go ahead. Dr. Ayman.
Thank you, Dr. Muhammad. Just some people are asking about the slide. If you want, if you can share it with the audience.
Uh,
Uh,
at some point, we can't because there is something that we have not published yet.
okay,
Yeah,
okay,
yeah. So,
okay,
sorry about this.
okay,
If you have any question, please just come to my office, and I will be glad to share it. If you are from Qatar, okay.
okay.
Dr. Ahmed Abdullah, do you want to say something? Please go ahead.
Thank you, Dr. Muhammad and Dr. Ayman. Excellent presentation. And again, this is an excellent research collaboration locally between Tamook and Center for Advanced Material, and also with the University of Waterloo. And looking forward actually